Welcome to the studio. Transitioning from hobbyist tinkering to industrial design requires a machine that can bridge the gap between a desktop and a production floor. The Bambu Lab X1 Carbon is an incredibly agile, high-fidelity prototyping station specifically engineered for industrial-grade manufacturing speed. Operating this ecosystem effectively requires an understanding of the hardware architecture, the material science, and the software-driven workflow. Coordinating these elements makes it possible to iterate on complex functional prototypes 3 to 4 times in a single day, rather than waiting 24 hours for a single version. Precision starts with the Core XY motion system. Core XY is a mechanical arrangement where the heavy stepper motors remain stationary on the outer frame, rather than riding on the moving axes. By keeping that mass off the toolhead, the machine maintains high-speed agility. This reduced weight allows the toolhead to reach a maximum acceleration of 20,000 millimeters per second squared. The extrusion system features an all-metal hot end and a hardened steel nozzle capable of reaching 300 degrees Celsius. That thermal capacity is necessary for printing abrasive, engineering-grade fibers without wearing down the nozzle. Integrated into the toolhead is the micro-LiDAR sensor, serving as the eyes of the machine. LiDAR is a sensing technology that uses pulsed laser light to measure distances and map three-dimensional surfaces. It uses that laser to scan the first layer with a 7-micron resolution, verifying bed adhesion before the print continues. This system also automates the calculation of extrusion flow rate, the exact amount of plastic needed, removing the need for manual calibration. This architecture automates machine maintenance, focusing instead on rapid iteration. The enclosed heated chamber and hardened components allow the use of advanced, functional materials that go beyond basic aesthetic plastics. This matrix categorizes the materials into 4 groups based on their industrial applications: composites, engineering, support, and aesthetic. Carbon fiber reinforced composites are used for high-strength structural brackets, while engineering plastics like ASA or polycarbonate are utilized for UV-resistant outdoor enclosures and high-heat components. To manage these filaments, we use the Automatic Material System, or AMS. The AMS is a motorized hub that sits on the printer, feeding up to 4 material spools into the hot end. Its critical application is managing support materials. Using PVA or breakaway filament, it builds temporary structures from specialized interface material, allowing the creation of complex geometries and steep overhangs. It is important to distinguish between these use cases. Using a standard aesthetic PLA for a part intended for a high-heat environment will result in structural failure. Utilizing the AMS for these specialized support interfaces ensures a clean surface finish on the underside of geometric features that are otherwise difficult to manufacture. The workflow begins in Bambu Studio. To maintain industrial standards, we use step files rather than STLs. A step file is a 3D CAD format that stores true mathematical curves and surfaces rather than a mesh of flat triangles. Comparing the two shows the limitation of the format. The STL sphere on the left uses a faceted mesh that ruins dimensional tolerances, while the step file on the right preserves the original CAD geometry. To prepare the print, drag and drop the step file into the slicer. Within the software, you assign the primary material to the main body of the model and the specialized support material specifically to the interface layers where the part meets its supports. Preserving those mathematical curves throughout the slicing process ensures the final physical part matches the dimensions of the original design. Before launching the print, ensure the checkboxes for vibration compensation and AI monitoring are active. The machine begins by vibrating its toolhead to tune its internal motors for the specific resonance of the frame. This tuning prevents ringing, a visual artifact that appears as echoing ripples on the surface of high-speed prints. During the print, a neural processing unit, or NPU, monitors the build plate. An NPU is a specialized microprocessor designed to run machine learning algorithms, which the printer uses to recognize the visual patterns of failed, tangled filament. If the camera identifies a spaghetti failure, the printer pauses the job and sends a notification to your phone. This automated monitoring allows the print to proceed without constant supervision, reducing the risk of wasting a full spool of filament on a failed job. The resulting prototype comes off the build plate, with the rigid support interface holding the geometry in place. Because the support material does not bond to the main part, the structure snaps away easily, leaving a smooth surface finish. By combining hardware agility, advanced material science, and a software-driven workflow, you can produce industrial-grade parts in a single day. Your first assignment is to download the bridging and tolerance test files to apply the principles of design for additive manufacturing, or DFAM. DFAM is the practice of designing parts specifically to take advantage of the strengths and limitations of 3D printing. Mastering these automated systems allows for a direct path from a digital concept to a physical reality, expanding the boundaries of what you can manufacture.